Okay, we're going to kind of deep dive on class, and some of it will be a little bit of review. So I know some of you will kind of know most of this stuff, but there really are a lot of little things around the edges with classes. So I'll try to throw all that stuff out so you can kind of soak up what you can. So you can think of it like a review, but I think maybe we'll cover some new stuff. I really like this stuff because some of this stuff was quite a mystery to me when I was just like figuring out what's going on. Why do I have a bug? So hopefully this will save you some time. Oh, right. Sorry. Sebastian wasn't in. Thank you very much, Eric. Um, so let's go ahead and talk about reminders. So we have a lab today. So this is a linked list treasure hunt. It's just kind of going to test your understanding of pointers and instances today. It's not super crazy, and we'll go over everything you need. And then lab 4, I just did publish this. You might see an email letting you know it's out there. I do need to reorganize the teams. So we're going to use Canvas groups for this. It's kind of a kludgy feature, but it's the only one we got. But give me like, tomorrow morning to sort out the group. So the way we're going to do this, it's going to be kind of a semester-long dynamic collective project. It's going to be a little messy. It's kind of a low-risk kind of thing, but hopefully you get some fun out of it. And we will do it in parts. So first part will be due this Friday, super easy. So it really is just a matter of finding your teammate or teammates and submitting a file that is a kind of a skeleton class. So it's going to be a little bumpy getting started, but we should be able to discuss it in a little more detail in Thursday's class. And of course, on Tuesday next week, we have both homework 1 and quiz 1. So I know there's a lot of stuff out there. I'm not going to be super hardcore on the Friday deadline for this, but I would like, it's just creating a class, right? So it really is, can you get with your team, get organized and submit a file? That's really all it comes down to. So, but I would like to see everybody kind of submit a skeleton class so I can put together a compilable program by our class on Tuesday. So that's really my goal there. So don't forget, there's no late policy on your quizzes. So you kind of want to get that stuff knocked out if you can. So for today, we'll go over a few hints and we'll remind ourselves how memory works, dive into our classes. The idea with an instance, I always think of it this way. It's a box with stuff inside, and the stuff is either going to be a data member, or it's going to be a pointer, or it's going to be an actual array of something. It might be another instance of a thing, right? So we don't really know all the stuff that's inside the box. We tend to refer to that as encapsulation when we code in an object-oriented way. So we'll just remind ourselves how we reach inside of the instance of some class and pull stuff out of there. So the whole class gets created, of course, by its constructor. And when we reach into the box, we can reach in 2 ways. We can kind of reach in directly to an instance, or we can follow a pointer to get to the box. And so that's really the mystery of dots versus arrows is what I call it. So we'll try to unravel that again for you today. And if you remember, it's either going to be an instance dot member or an instance pointer. That should really say instance pointer arrow to the instance member. So we'll review what that actually means. So these are, of course, all members. Now that box exists in memory. Everything that exists in memory has a pointer, so we can get the address or the pointer of the entire box. But things inside of the box might be something else altogether. So we'll try to demystify that, right? We'll go over our methods, talk about what those are again, remind you of what it means to pass an entire instance into a method. So we could have a method in this box that receives a copy of another box, which seems kind of doesn't fit the physical world very well, but in code, that's okay. Like I can be an instance of a person with a method that processes another person. So we'll remind ourselves how those things actually work. And the different ways we can use those. We'll also dive now into this. So this is something we've kind of skipped in previous classes, but it's something you really want to understand. Many languages have a concept of this, which in the beginning is like, what is that thing? So we'll try to demystify that for you. And then we'll pull in this strange thing called struct, which many of you might know. That's what I started out on before there even were classes. So before things were really object oriented, there were no classes whatsoever. There were just structs. So we'll just review the difference between those two things, and that should get us to our lab 3 for the day. So, insights from last week. Outstanding work, everybody. Those were some good little challenging labs. Thank you for your patience with some of the back and forth. None of this stuff, you have to worry about everybody having this memorized, but there's some good fundamental things to remember around precision. First off, whenever we declare a variable, we take up memory, right? And that variable, if it's declared that way, it's kind of inside of some curly braces somewhere most of the time, and it kind of comes into existence and then goes away. But it takes up space. So an integer is 4 bytes. Each byte is 8 bits. So when we lay out variables inside of some scope like main or a function, we're really just sort of taking up regions byte by byte by byte, more or less. And those individual bytes are, of course, 8 bits. So no one needs to memorize this, but it does help us remember why certain variables hold more precision than others. And it also helps us remember that when we make an array, really all we're getting from the array is going to be like this two array here is the beginning of the array, right? So here is an array with 2 positions in it, and each of those positions takes up about half of that space. So a long is comprised of 1, 2, 3, 4, 5, 6, 7, 8 bytes. So that's 8 times 8, that's 64 bits. That's the biggest possible value we can have in C++ on modern architectures. Now, some architectures will have like exotic stuff that goes beyond 64 bits, but the vast majority of our computing devices today are 64 bits, and very few of us remember probably when phones were 32 bits. It wasn't that long ago. It was a real pain, but now they've caught up with all of our desktop machines, which are all pretty much 64-bit architectures, okay? So when we check for the size of, now don't confuse that with dot size method, but the size of function in C++ tells us how many bytes. So for some of us, we might have been surprised a little bit at some things with our precision, but our size of is always an interesting way to just kind of go, hey, what size is that particular thing here? Okay. So there's my kind of 1 byte comprised of 8 bits down there in the corner. Now, when we get the address of any variable, we are getting the location of the first byte, more or less, of that particular variable. So we're really just, by virtue of that int I being an int, our pointer is kind of telling us where to begin slurping up these bytes. And as you can kind of guess, that integer is spread out across all the bits in those 4 bytes. So pointers, because they have to be able to send us to any location in memory, must have the exact number of bits that the architecture has. So if we're on a 64-bit architecture, our pointers must have enough space to articulate every one of those addresses in memory. So we can jump anywhere we want in memory and go find something. So that's what a pointer really is. It's a number, but it refers to locations in memory, and there needs to be a lot of them, right? 2 to the 64 possible places that we can go find stuff. So an array is nothing more than sort of packing in whatever that array is. So here we've packed in a long, but we could have an array of pointers or an array of integers or array of characters. So the width of our full array is going to depend on whether it's comprised of characters or longs or pointers or whatever. And that's really what's going on in C++, okay? So just having a general idea that these things take up memory, and when we declare them is when they, exactly grab onto some memory. And when a function is done, they all go away, right? They're all released back into the wild, and somebody else can lay out this memory in a different way, okay? So that's kind of the first little mystery to be aware of that's going on underneath all this stuff, right? And so now there are some alignment issues if you really dig down, and it's not too hard to find them, but the order of the bytes, high order, low order, like which is the highest order byte? Is it over here, over here? You'll hear people refer to big endian, not Indian, but endian, big endian and little endian. That depends on whether your architecture stores the bytes in high order or low order sequence, okay? So this is all just good information to have, right? You will definitely run into this if you keep coding. I'm not going to run right out and test you on all this stuff, but it is really, I think it's fascinating. It gets to the lower level architecture that sort of sits below us. Now, for most of our labs, some of the insights that we got when we calculated the average was just about managing precision. So I should have been more clear and put this in your main section. So setting precision in the output stream doesn't give us more precision in our math. It just shows us more precision. So the precision was always there. I just forgot to load the IO manip library and then print out more digits in base 10, right? So we need to do that. And then we can sort of say, hey, how much precision does the average variable have? That gives me the number of bytes. This precision down here is how many decimal digits do we want. So these are kind of two different systems. One's in binary and the other one's in base 10. But more or less, if we just do this part down here, we can kind of see what our actual value is out here. And if you don't see zeros, it's probably a repeating number that has never really kind of resolved itself, right? Like 1/3 or something like that, okay? But we won't really dig that deep all the time. It's just kind of interesting to know what's right below our feet there. So a couple things, many of you I think knew this and probably just had a moment of insight. So if we did just that, right, and we did that, we're getting integer division in C++. Kind of annoying. It just sort of ignores any of the floating point stuff and gives you an integer value back, even if you're assigning to a float. This equation right here gives us an integer result. And then, yeah, sure, we can put that in an int value, or float value, but it's not going to save us from losing our precision. So for those of you that got a flat 50, that was a quick fix, not a problem. Lots of ways to get around it, right? We can multiply the numerator by 1.0, forces the numerator to be a float. Now we have float division. So that's one way to move ourselves into a floating point answer, right? And then, of course, we still need to either assign it or return it and have a float function so it doesn't get clipped on the return. But that's kind of how we would kind of get around, one way to get around that problem, right? We can still have an int, but force the division to move into the floating point realm, or we just sort of convert our sum into float so that our division automatically migrates over to that floating point form, okay? Now, some of you went even further, which is great. So float doesn't have as much precision as double. So some of you said, well, I'll just sort of kind of do my sum in double space, divide it by an integer, and that will do the actual division in double space. And you'll get more accurate result, even though you're going to chop off some of its precision. You'll still get a more correct answer, because all of the math is sort of happening in this double space here first, and then and we're accumulating in double space, etc. So there's lots of ways around this. And, if you just want to make everything double, that's perfectly fine. That way you get the most highest precision answer you possibly can, right? So I always think of, again, these self-driving cars, I hope they're using double precision everything in their C++ code, so they know exactly where the corner is, okay? Now, I know we talked about this, but just a reminder, this is due next week. So please do remember, and if you haven't started yet, just get your data members up there, right? That's the easiest thing. And then think about whether they're public or private, and just sort of go from there. So I won't kind of go over this too much, but you should be able to create an instance of the ball, put it inside of a loop, and then call your two methods iteratively to just kind of get that thing moving around. Okay, so maybe we'll have some time to kind of dig into that at lab on Thursday if people have questions. Okay. Okay, so let's talk about classes. So classes, of course, allow us a way to model a problem with lots of classes. So, and we want to not be thinking about all the details all the time. So they're like nice container boxes. We can sort of put away our thoughts, worry about the interface, and stop worrying about all that stuff we did 2 weeks ago, okay? It also means that people that interface with your class, like in our Lab 4 risk game, just care about your interfaces. They don't care how hard your job is. They're like, just make the dice, all right? Like, I need to roll the dice. I don't care how you're doing it. Just give me an interface, give me some comments and some documentation so I know what to do. So that's a very nice thing to do, right? And those things are exactly like structs, but we'll see today that it just has different kinds of access, privacy controls than a class. So we could be using structs this whole time, but we're going to use classes because that's basically what we want to do. So our class is like a factory, of course, and we're just cranking out copies of stuff from our factory. But as we will see in this class, there are variables in our class that describe the instance, and then there are variables that describe what's going on at the factory. So we call these static data members of the class. And we really haven't done much with them, but they're really cool. So if I have a car factory, I want to keep track of how many cars have been produced so far. I want to give the class a static data member so that I can keep track of stuff like I have a chalkboard at the factory that's separate than what each car has, okay? So every language has this concept, modern language has this concept of static class data members and non-static. Static is just a fancy way of saying it's in the factory, not in the car, okay? So it's a blue car with 4 wheels and lots of gas mileage, but that's different than how many cars we actually produce, okay? And a lot of cool things can be stored in the factory. You can have functions or methods that are in the factory, not in the car. So the car can accelerate. That might be an example of a method, but the factory might have something that creates 20 cars at random, like a special method in the factory that knows how to produce certain kinds of cars. So there are lots and lots of cool things we can do with these static methods and static data members in our class. They just don't end up in our class itself, our instance of the class. So we've all seen the code. So we'll do our person example. Don't forget the semicolon. It's always easy to forget that. It's one of the few kind of things where we put a semicolon after the curly brace. And remember that we tend to have these major areas for public and private stuff, okay? So I know my colors get a little messed up, but all of the stuff that we want to do in main, we put, of course, in the public area. Stuff we don't want to have access from main, for example, we put in our private area, okay? Now, classes are pretty similar between C++ and Java. Some of you have taken Java. Some of you have programmed in JavaScript or other languages. A lot of these languages have evolved to be relatively similar. Python is kind of a little bit of a holdout. I won't throw that one at you. It's similar concepts, relatively different syntax in Python, okay? But the idea of constructors and private and public are kind of useful concepts that transcend any particular one language. That's kind of reassuring because it means it's not so hard for us to kind of pick up another language once we understand these primary concepts, okay? So here would be our first warm-up exercise. Feel free to click into this if you want to, but the idea is just to implement the class and fill out the to-dos, right? So I'll just sort of show you this. I know most of you know how to do this, but if you were to sort of click into one of these things, and I'll turn off this thing so I don't burn everybody's eyes out. But right, so remember we put our data members up here. And when we're working inside the class, we do not reallocate the data members. I don't say string first name equals something because I've already got string first name up there. Sorry, that's so small. Let me make that a little bigger for you. Okay. So we do not want, we're going to declare the data members here and refer to them down there. Don't put an int here or a string because that will mask or shadow over the top of your actual data members. It's not going to change this if you create a brand new mailbox, right? That's the thing we use to talk about in our beginning class. So watch out for that. And as we'll see today, watch out for the fact that you don't really want to use the same name here that you use here. Choose something else for this one. We'll see in just a minute, okay? That way, C++ knows that this is getting stored in this, which is really just a reference to that up there, okay? Flows in this way, down here, and then over to there. So that's really what we're talking about. And then, of course, the print me is allowed to have access to those data members. That is perfectly fine. So let's look at one implementation solution for that, right? So there's our kind of first name equals F, last name equals L. Notice, of course, it's okay in C++ to cram stuff all in one line, right? It's a little bit, abusive of me to do that to you, but it's kind of nice to fit it all on one screen. And then here's me grabbing these things up here, right? Right? I'm just reaching up to the top. Okay, so many of you probably in algorithms, when these things got really huge, you forget, oh yeah, I'm inside of a class. So I got to go all the way up and figure out what my data members are, right? So this thing is inside the class, of course. Many of you, I think, probably remember that pretty clearly from recent coding experiences, okay? So you should be able to kind of do that, kind of fill out those things, right? And if we looked at main, sometimes we can kind of see what main wants. Main is trying to access our print method or something like that, okay? Now, our access modifiers, we haven't done a lot with, but out in the real world, most data members are private, and they give commercial software the ability to protect itself from abuse and accidental misuse, okay? So public is okay for the constructor and okay for the methods, but increasingly, as you kind of get into professional software, you'll see that the actual data members, the individual variables are not public, right? So we always have getters and setters. We talked about getters and setters being the public way that our methods actually modify those things, okay? So, but we'll kind of do a little bit of both in this class just to kind of keep things a little bit lighter along the way. Now, in main, hopefully we all remember, right? So think of this as like int x, right? Except it's person for Mickey Mouse. But when we call the constructor, we got to pass it whatever arguments it has, right? So Mickey Mouse would actually go, of course, with our first name and our last name, right? So Mickey Mouse, right? So those have to be string variables, okay? So back over to here, right? And so that's us creating an instance, not a pointer, but an instance by calling the public constructor, okay? And if we don't put the constructor in the public area, well, that will fail and nothing will really work for us. But person is like the type. Really, it's like a type, but it's really a class. And we sort of look like we're using it like we're creating int x, but it's just person and then and then our constructor arguments, okay? So that's the pattern we're going to follow. And that's specifically because person needs two arguments, right? So we got to do that, okay? Now, once we have our instance, so there's our kind of instance again, right? So we can use the dot because there's no pointers in that main code right there. You don't see a star, you don't see person star or a new or anything. You just see person, right? So that's a clue that you're going to be reaching into the box with the dot. So DD, sorry, that should be typo there. Give myself a little warning. Go back and fix that. Or last name. So if this was public, we could do it, but here we have that private one. So that's going to generate an error for us. Okay. So just really demonstrating how that works. And of course, we can call our print me method and we don't put the DD in the parentheses, right? Because it's object oriented. We're saying, oh, print me knows what it's working on. It's working on the DD. Okay. So again, those should be DD right there. Okay. So I think probably everybody remembers that stuff from last time. Remember, of course, that our assignments sort of go from left to right there, right? So we're just putting them in the data members and we should be off and running after that, right? And those are the same things up there, okay? So it's clear that that's what we're kind of working on, okay? So, yeah, worst bug you can do is put the word string right here, right? That has caused many people to lose some sleep trying to get their homework to work. It's a silent killer because it's like, well, I'm pretty sure I said it, right? But it's still crashing, right? So watch out for that. Okay, so when we do this, again, just remember person is the factory, the instances are what we create, right? And so they literally actually carry with them not only the data members, but remember that the actual code for the print me lives inside the instance, which is kind of weird. So the actual code essentially for that print me is duplicated in every instance. It's not back at the factory over here. This is just the sort of template. It's actually putting those things in there unless they are static. So when we get to our static variable types or static method types, then it'll stay back at the factory. But right now, those things are copied into each individual instance, and they actually take up space. So your instances are going to be fatter if they have more methods defined in them that are not static. Okay. So when I call dd_print_me or mm_print_me, it's calling that actual code inside of that instance. Yes.
I'm just kind of refreshing my memory. To get a private variable, we would usually make like a getter thing.
Exactly. Yeah. Yeah. And we'll see a little bit of that. Yeah. So you could think of the print me as kind of a getter, but it's not really a getter because it's not returning anything in this case. Yeah. Yes, exactly. Yeah. And there are a few over the semester, we'll see only a very few data members of classes from containers. There's one called the pair container or the pair class, and it allows us to have public access to its data members, but it's pretty unusual otherwise. Most things require some kind of getter. So, of course, people use lots of ways to describe this. They'll say, I create an instance of a class, or MM is an instance of. So some interview questions, that's a very common thing. They'll say, well, what is a ISA? ISA is a person, right? It's easier than it sounds. It's like, it's just an instance of a person, okay? Or sometimes refer to an instance as an object. Those are kind of interchangeable. People might argue about that, but an object is kind of an instance of something, okay? I like to call it a variable because in C++, it sort of syntactically looks like a variable. Int x, person x. Those look like variables, except for the constructor parentheses on the person constructor, okay? So let's talk a little bit about our constructors. They, of course, build the instance, right? And the return value from a constructor is an instance, right? There is no real declared type for constructors. It's sort of understood they're returning an instance of whatever class you're inside of, okay? Now, it has to be public, right? But it can access, the constructor, of course, can access both public and private members of itself, which is perfectly fine, right? And we can have lots of constructors. So we could have lots of flavors of constructors. Let's say you have a constructor that opens a data file from a chess game that you're halfway through. That constructor wants a file name, right? Versus a constructor that starts from scratch, right? So that one you might just give it no arguments. And it'll be like, oh, I'm going to start from scratch. You didn't give me a file name or any kind of history. So we can overload our constructors however we need to do that, okay? And if we don't even put one in there, C++ silently creates an invisible one for us. Doesn't have any arguments, but fortunately, it will create an instance. So for your lab 4 for risk, if you have to do like a roll the dice class, just, call it roll the dice and you're done, right? Give it 2 curly braces and a semicolon and you're off and running. And now you can create an instance of your class. And a lot of times when I'm roughing out some multi-class code, I will just do it exactly that way. I'll just throw out a bunch of class names, create some instances, and go from there and sort of iteratively refine that. Okay. So the only thing to watch out for when you create multiple overloaded anything, constructors, methods, functions, is you have to have a unique function signature. Now, these constructors don't return a value, or they all return the same thing, really, an instance. So we got to watch out that we don't have any that have the exact same number and type of arguments. Doesn't matter what we call the arguments, but if the number and type matches, we have a collision, and that's a problem, okay? So that situation's okay, because we have kind of 1, 2, and 3. So that's easy enough for the compiler to tell which one to call, depending on how you invoke it in main, right? So that's okay. We'll come back to some gotchas on that. Remember also that we want to, not have the exact same names, right? So this is a different name. It's being assigned to this, not the other way around. Sometimes we get those things backwards, okay? but we don't have any type over here. But otherwise, it's very much like a function inside of our class. Okay, so I think everybody's probably seen that before. Okay, and there's no, of course, return statement on that. Okay. Now, if we do this, we create a bug for sure. Python will probably do the wrong thing. Python, sorry, C++ will do the wrong thing. So it doesn't know which of these things to work with. So what it really does is it goes local first. It says, okay, this is going to get itself, right? So it really doesn't ever even assign it to the data member. It assigns it to itself, right? So that is a problem. So we don't really want to do that. So we got to watch out for that, right? And we'll show you a few fixes for that. One of them that's very common is just to put an underscore in front of this, right? That's one way to follow a rule, right? We just got to make sure we don't do that. So that is one way to fix that problem, okay? You don't have to like burn brain cells figuring out what to call it. Just put an underscore in front of it and you're good to go, okay? We can also use this. So we'll talk about this in a little bit here, but this, a lot of us is mysterious. It's like, if it's optional, why should I use it? Well, it clarifies what we're talking about in this particular case. It's like now C++ knows we're talking about the data member inside of this instance that we're building. So our robot is actively building this instance. So this is a short for the current instance the constructor is working on. So fix this data member to be that. So that's one way to get around that particular problem. And many languages have this kind of interesting concept of this, okay? Just sort of makes things a little more clear, but there are a lot of places where we don't need to do it. And it's a pointer. So therefore, I'm going to use an arrow, not a dot, okay? Pointers to instances are followed by arrows, not dots. That's the only real rule we have to follow, okay? So that gets us into the box, and now we can reach in, grab the first name or the last name or some method that we actually want, okay? So we really only ever use this when we're inside of the constructor or inside of a method. It's the only time you're ever gonna see it, okay? You can think of that robot arm building the instance of the robot. That's what it's actually doing, okay? So as we mentioned, you can have lots and lots of constructors, but we got to be really careful because this situation is a problem. So we see first name, last name, and we think, oh, these are different, but all C++ sees is this and this. And it's like, hey, these two things are the same, okay? So if we tried to create an instance of a person with just one string argument, how does C++ know which of these to call? That's why it complains. It's like, hey, I can't tell what you want me to do, and I'm not going to flip a coin. So that's where the compiler kicks in and says, you know, that's bad. So we just can't do that, okay? So that's just a little heads up. Probably won't run into that too much. The other slightly mysterious thing is, so here's something I would call a default constructor. It's got no arguments, okay? So this is unique to C++. Python doesn't do it this way, but if we have a constructor that doesn't need any arguments, in C++ we create it just like int x, person John Doe. No parentheses, no empty parentheses. If you put parentheses after that J-Doe, you're going to get a very strange C++ error, and it's going to be somewhat confusing what you did wrong unless you remember no parentheses if you're calling a constructor with no arguments. Not a big deal, but when you don't remember, it's like, what is going on? I don't know why I can't create an instance of this simple class right here, okay? So that could come up in your initial risk classes when you start roughing those things out, okay? So if you did that, we would have some problems, okay? Now, if we had another constructor that was overloaded, that supported several arguments, okay, that would be fine, right? But we don't have that here, okay? So if we wanted to enhance a class for brevity, I'll kind of ease over the top of this one, but there's a lot of work here, but these are those getters and setters we were talking about, right? So if I have data members, typically we will name our methods after the data members. But of course, they are not the same thing, right? Get age is going to return the data member age, right? And get first name is going to return the first name. So the type of the getter is got to match the type of the data type. I mean, generally it will, right? First name, last name, string, is alive, Boolean, that kind of thing, okay? So you all may remember that from our car homework assignment in Comp 130, or if you've done similar things in other classes, okay? So if we wanted to create two people, right, we can kind of do that relatively easily. We can use our default constructor to do that, right? Okay. So let's just look at the solution code for that. But keep coding if you're doing that. I'll try to kind of slow my roll here just a little bit, but kind of get some highlights out here, right? So we have our Boolean is alive, and we have our constructor, our default constructor. Now, a lot of times people will ask with good reason, it's like, well, if these are values we can put in them up here, why do we even need to do anything down here? Can't we just leave that blank and move all these values up there? And the truth is, yes, you can do that in most cases. There's some situations where you cannot do that, but we can do both, right? If we're in doubt, we can put it in both places. But sometimes I'll just put it here so I know for sure, okay? And then here's my overloaded one with more arguments, etc. Okay, and then my getters, okay? And now we're off to the races, right? We kind of got things going, okay? Okay, so hopefully that feels kind of comfortable. And remember, these are inside of the class, right? The whole class is here, okay? And that's really just the factory. We haven't created anything yet. We got to go to main before we actually, create something, okay? But that's our fully specified, well, mostly fully specified class, okay? So come back to that one if you want to practice that a little bit. Let's look at our methods, or some people call them member functions. So of course, these are just things that are part of the class. And as I pointed out earlier, they're actually inside of every instance of the class. So if I create an instance of a robot, it's got all of its method code in it and it takes up space. So if I create a million robots, I got a million print me functions out there, which maybe that's what you got to do, but there are situations where you could kind of leave the functions at the factory, so to speak, okay? But most of the time, we just throw them in there, and, it's not like we're creating that many instances that we have to worry about it, okay? But all these things can be overloaded. They can be public or private, just like we saw with our other data members, okay? So you might think, well, why do I need a private method? Well, maybe you need to do some calculation on the area of a sphere, right? Or area of an ellipsoid, or I don't know what, right? So that might be a private method inside of your geometry class, for example, that you don't need anyone else to know about, but you're going to use it in your other methods, okay? And just like our constructor, we can overload our methods. So let me just remind you of one trick very quickly here. We'll kind of breeze over this so we don't drag everyone down too much today. But notice that we'd like to be able to just print something about a class versus maybe put a prefix in there. So our first temptation might be to fully write both of these and duplicate a lot of code, right? So both of these at first glance might need the exact same code. It's just that one of them has a prefix, right? But we'd like to be a little more optimal than that. So we should be thinking how we never write the same code twice. That is a goal of every kind of advanced programmer. If you ever see yourself writing the same code twice, take a moment and see if you can refactor or restructure your code in a more optimal way, right? Because we're all going to make bugs, and you don't want to make twice as many bugs. You want to make, one bug if you have to. So one way to do this would be to daisy chain these things together. This one has no arguments. It calls this one with a blank, right, for its prefix. And then we have another one down here that actually has the prefix argument. It's okay. It's not the best way, but it works, right? So we have an overloaded version of our method, and we're calling this one from this one, right? And we're just being a little tricky and giving it a nothing burger right there, okay? And we're referring to our data members directly from inside of the print me, which is inside of the class. Okay, that's perfectly fine. Not the most optimal, right? The next kind of evolution of this, it's called eating your own dog food, is it's like, hey, well, what if we decided to change first name to first underscore name? Well, if we change the data members, that's going to break our print me method. So why don't we just call our own methods? So the print me here, in this case, is calling its getter in from inside of the method. Notice there's no like arrow or dot. That's perfectly fine. It's like, hey, go get me the first name. I don't even know what it's called, but I remember what the getter method is called. That's okay, right? So print me is kind of testing out somewhat unintentionally its own methods. So a lot of users get annoyed when software development companies don't test their own methods. They document them and they ship them and they, they're like, hey, it's great. And it's like, oh my gosh, you expect us to use this stuff. Like you guys aren't using it, but you want us to use it. So this thing is a technique that forces you as a developer to kind of test out your own methods more kind of organically. Okay. Now, probably the most optimal way is just to use our friend, the default argument value, which hopefully you remember is pretty much common to all languages these days, right? So if we don't specify a prefix in our main or wherever we call the print me method, then it will automatically receive a blank value, which achieves our goal of like not having any prefix at all. So that's probably the most kind of optimal way to do things. And then we've got our getters in there, okay? Yeah, age, etc. Okay. And this is a ternary operator. We talked about this the other day, but if I'm alive, return the string alive, otherwise return the string not alive. So a really just concise way to avoid having to write yet another if else chunk of code. Okay. Okay, all right, moving through it. Okay, instances as arguments, still review, I know. If I had this number class that sort of abstracts and kind of creates a concept of A as a number or a variable and B as a number variable, and we're feeding a 1 to that constructor and a 2 to that, how do we add the B to the A, right? So we want to be able to pass the instance. We're not passing a pointer to the instance here. We're actually passing the entire grocery box through that doorway. It's like, here's your groceries. I don't know what's inside of there. You deal with it, right? So we need an add method that expects an argument of type number, right? It's got to be number because that's what B is, right? So let's look at the code again to refresh. So we have our private val there, right? Here's our constructor, right? Here's our getter, and here's our adder. So we're getting a number, even though we call it N here, it's really that box of groceries that we passed in from B. And technically it's a copy of the box of groceries. So it's not even actually the B, it's a copy of the B that we've just received, which might be a surprise to some of us. But now we can say, okay, I will take your val from that copy, add it to mine, and put it back in mine, okay? So notice I'm not returning anything, right? I'm just saying I want to add you to me, right? So that's A add B, and now A should be a 3, right? So if I could print out that thing, I could do that. And I can also flip that around and say B add A, perfectly fine, okay? So hopefully that rings a bell. And remember, those are full instances, heavy boxes of groceries that take up space and get copied. So that approach to passing in B or A is not terribly efficient in truth. It is forcing a copy to exist for a brief moment in time, and then it gets thrown away. So really high-end C++ developers would look at that and go, oh, don't do that. That is just, who knows how big that A or B could be, right? And we'll remind you of some the more optimal ways to actually do that, okay? Okay, we can do that, right? We can add that method. I'll just, again, kind of breeze over that a little bit so we leave ourselves some time for our lab today. but you should be able to come back and fill in these little gaps to kind of get this code working, right? So let me just take a peek at that, see what we actually have that you have to fill in. Oh well, I spoiled the ending. Well, here's the main, right? So we're just kind of doing the addition of those things. And then here's we kind of saw the code, but like here's all we really need to do here. And of course you can call this anything you want. X, Y, Z, Q, whatever. Other. Some people call that other. It's like, this is the me and you are the other, okay? So back in our main section here, in this scenario, where did it go? B is the other and A is the me, and now A is the other and B is the me. So hopefully you've kind of had to do this mental gymnastics before, when you're thinking about coding the add method, you have to kind of think who's the me and who's the other, okay? That might be the most confusing part of it, okay? Okay, so that is passing an actual box of groceries, right? So now this is really interesting and good to point out. So notice this is private. That means, hey, only I should be able to have access to my data members. But guess what? When the thing that gets passed in is the same class, it's like, hey, it's family. Okay, so if it's part of the same class, we do get access to its private data members, even though that is a different instance, right? I am one instance I'm working on. You are a different instance, but if we are of the same family, I have access to your private data members. That is easy to forget, okay? Which is key, right? It's like, yeah, we couldn't write this very easily without that, okay? So that's a really nice kind of feature that exists. And I think most languages are that way, okay? So little key point there, okay? All right, so arrows versus dots. You can tell I have way too much fun with ChatGPT images. I got a Christmas present. So I have unlimited ability to create obnoxious pictures with AI. So, and I can tell you that this one took way too long. ChatGPT does not understand near and far or left or right. It really struggles. But this is the idea that I hope I can get across to you for those of us who might still be struggling with this. If this is our tiger pointer here, it is just an address. It's like, hey, there's a tiger instance over there. Okay, so that's what a pointer is. Of course, it's just an address. So we need to follow that address to get to the instance. So in that situation is where we use the arrow. Tiger pointer is hungry. So we're just sort of asking, is this tiger hungry over here? Of course, right? Okay. That is different than an actual instance of a tiger behind you that is hungry. In that situation, it's not a pointer, it's the actual tiger, and it is tiger dot is hungry. So we'll review that here in a second, but that's the big message is just, are you dealing with a pointer or you actually have the tiger? Okay. So let's take a look at the code. Inside of some curly braces, main, a function, an if statement, a while loop, it really doesn't matter. And you can even just do that for the heck of it in the middle of your code for no good reason. You can throw up a pair of curly braces and create a neighborhood. I'm going to create an instance, right? Another instance and another instance. Okay. And I do stuff with them. And then since those are automatic, they have variable names and there's no new in there. There's no pointers in there. They are going to go away automatically. So after execution leaves that second curly brace, everything that was created inside of there, of course, is going to go away. Okay. And that's a good thing. Saves memory. We just kind of use up memory when we need it. And then those variables go away. So if I did something crazy like took the address of this and passed it out of here, that could be very dangerous. And that's why a lot of code crashes. Okay. So understanding this behavior is so helpful, right? It's like, hey, those things are going to go away. Not safe to talk about them after we leave that scope. Okay. Now, the other scenario, though, is this one. I have a pointer to the tiger, right? APTR star, right? This is a pointer or an address, 64-bit, pointing to that kind of a thing. And now we create the thing, right? Give me back the pointer so I can store it in that variable. That's what new does for us. It creates the thing, And then, so there's the address, and it gives us that address, right? And so we say this is pointing to that, but we're really just holding on to its location. It's that faraway tiger picture we saw, okay? So one scenario automatic, this scenario not automatic. This is what we call dynamic, right? And we can do this all day long, right? Create lots and lots of stuff, okay? And then when we call the methods, we follow the arrow, okay? It's the faraway tiger situation, okay? Different than the dot, okay? And you might note that these things do not go away. So this would be a memory leak if we cared about it. Like if we were in a function and we did this, well, A, B, and C are still floating around in here, even though these guys are going to go away, okay? So when we leave this scope right here, these go away, but these guys stick around and take up memory, okay? And that's a leak, right? So that's a bad thing, right? Just because these guys go away because they were declared here doesn't mean that these guys go away, okay? So that's an important insight as well, okay? Okay. Okay, so if you want to try this one, let's try this one. This one is quick enough, right? So we want to make an instance of this class. It's just called random value, called A, and then we want to create a pointer to a random value. Notice this is not creating an instance yet, right? This creates an instance. This just creates space to store an address that's eventually going to point to an instance, okay? So we want to do that in our code, okay? And then we want to assign PTRB a new instance. So we're going to use our new to do that, right? So this one should be pretty easy. I'll check the code here with you in a second. And then the test, like this is going to be in your quiz, right? Can you copy from one thing to another, right? So how do I copy the value from B pointer over into A, right? Or vice versa, right? I think that's what we want to do, okay? So let's just look at what we want to do, right? We want to copy that thing over there, okay? So it's really going to be B pointer arrow value equals A dot value, okay? So if you can kind of unwind that logic, then you're probably in pretty good shape. And then, of course, print those things out to make sure that you actually made that change, right? So we're looking for something like this, right? So there's our pointer, automatic, just a pointer, right? So both of those will go away. This one will not go away. Well, at the end of our program, it will, but if this was a function, it would be a memory leak, right? And there's our copying this thing over to there, okay? Okay. So if that makes sense to you and you can kind of work your way around those things, then you're doing pretty good, right? Pointer, not pointer. Instance, instance, okay? Questions on that one? Okay, all right, really dense stuff, but man, this is good stuff. If you get this, man, you've got a leg up, which is really great, okay? So there's our kind of pointer versus, the other one, right? And then we say this is heap memory. This sticks around, okay? So these would be a function call or some if or some while, okay? And those things go away, right? That thing does not. Okay. Okay. All right. So I think we're doing pretty good here. Okay. So let's take a look at what this does. So let's think about this for a second. That's an array with 10 positions and it holds pointers, but we haven't really initialized those pointers. So we should assume they're junk, right? But we know we have space for 10 of those things. So this gets to our lab today, okay? So we want to understand this idea. So we're setting up like this bed of nails, if you want to think of each of those as a pointer pointing to something. So we're going to go through here, and for each position, we're going to create an instance of something, and then new always gives us a pointer, always, always, always. So we're shoving those pointers in there. And now it's like decorating a branch of a tree. Every position in the array is referring to an instance of the class, okay? Even our homework too is going to do this, right? So we'll be pointing to instances from positions of the array, okay? So it's kind of like this, right? Now in our lab today, I'm going to be devious and then randomly I'm only going to be pointing to some things and other things are going to be null. So you're going to have to go on a treasure hunt, first figure out which array position has got a good pointer and then follow it and get some treasure out of the little orange boxes, okay? So if you're not checking to see if the pointer is valid, then you're going to crash, right? So we'll see that here in just a few minutes, okay? But it's important to kind of be able to visualize this picture here, based on this type, right? Once you see all this code, okay? That's really a data structure, right? Of course, we're just building an exotic data structure that helps us store something that has meaning, right? Okay. And when we get to the bottom here, right, because of the way this code is written, we got a big memory leak. We forgot to delete these things, right? We created them and then we left them. And it's not so bad maybe that we didn't delete them right away, but we lost the array, right? The array that kind of helped us find those things is now gone and we have no way of cleaning up our mess. So probably this is just a design error. We really should have been given the array from the outside world, and maybe our function's job is to fill it up with pointers to instances, right? And then when we return, we've just updated the array that we were given. That would have been a better design, okay? But the way it is right here, we have kind of a memory leak, right? And kind of doesn't really serve much of a purpose really in the end, okay? So one more time, just looking over the top of these, right? So when we have an instance, we can add the age of that person to me, right? Or if somebody overloaded the method, now that we've refreshed ourselves on what a pointer means, we could say, oh yeah, this is just another flavor of that. So if you were a pointer, then I will use an arrow here where I was using a dot there. Notice arrow, star, no star, right? So I'm just saying, oh, I'll add your age to me. So this is just a totally valid second option of the same thing in case someone wants to give you a pointer. So what you're really doing when you design a class like this is saying, oh, okay, I'm going to be very conscious of what my users want. Maybe sometimes they want to give me a pointer, sometimes they want to give me an instance. We'll do both, right? So we add both. Now, if you try to do this, kind of remembering references. So references are not addresses. They're this special creature. It's like a link, a magic link. Whatever somebody gives you, that's really what it is, right? It's this sort of wormhole through space, right? Where the thing that you have in main is actually in your add method, okay? So nothing wrong with this by itself, but the compiler looks at this and it looks at this and it does not know which one you actually want to call. So if you've got both of these, you're going to get an ambiguity error and you'll be like, why can't I get this thing to work, okay? So you kind of just got to choose, right? Which one of those two things you want, okay? And we'll come back to references to refresh your memory on those. They're really powerful. Probably if it was me, I would probably go with this and this, because this is a very big box of groceries that gets copied. This is a pointer and this is a reference. There's no copies happening in these two right here. So they're probably preferred approaches over this one here, right? If we're just grabbing that age and putting it in there. Okay, so a little bit of reminders on references. So again, we'll just kind of gloss over the top of this, but if you wanted to implement that second one, you can kind of do it fully in code this way, right? So I think we saw that, but we can't fit that third one in there, okay? And in this case, no return value. I'm changing myself, right? I'm just changing who I am, not returning anything back to the caller, okay? We could write that as even another flavor of this, but we're not going to go into that today, okay? Okay, we're getting toward the end. I know this is dense, but we won't go past 7 guaranteed at this point. I kind of tell. So here's our main. So here's a couple insights here. So bear with me. So there is an instance. That's kind of the proverbial tiger sitting next to us. that's a pointer that isn't pointing to anything yet, but it will. Now it is pointing to a number. So I can create a third one, right? And I can say A, add A. So let's think about what's happening here. This is a little tricky, but important, especially for folks who are really serious about C++. A becomes a copy when it gets through that doorway. So what is received is not really A in that situation, given the code we saw on the previous page. It's a copy of A. Okay. It's like that science fiction transporter problem. Like, is it a copy of someone and then you destroy the original? Right. But we're just sending in a copy. So we're using that as a way to add to ourselves. So it's kind of a weird thing to do, but we can do it. If we do this, we call the other overloaded method because PTRB is a different type. So it's going to force the compiler to choose the other method, of course, because that matches, the method argument declaration, okay? Now, if I do this, let's think about that. I'll give you a moment to guess which one is being called there, okay? So in this context, ampersand is like a math operator. It's like a function. It's like, hey, I want your address. So it takes the address of C and shoves that into add, and the compiler says, oh, that's just like this one. So these two are going to call the same overloaded method in terms of the code sequence, okay? So we just got to remember that when we're in main, if you will, right, we're calling the methods. This is going to operate on this first, and then the answer to that is going to go into the doorway, okay? So like I always say, it kind of works from the inside out, okay? Figure out what that is, then send it down the pipe, right, to our method, okay? And then we can, if these things are public, we can kind of access them. Again, this is not a reference, so we'll come back to references like another day, but we're not going to drill into that too much today because it's just a bit too much. Okay. Okay. All right. So just kind of looking at these three things so you can compare. We could do this. We could do this. We didn't choose to do it, but it would be a good idea, more efficient than this one here, right? And we'll come back to how we use those things a little bit later. Okay. Okay, let's talk a little bit about this. Another fun picture. All right, so this is kind of, I think maybe everybody gets it, but I struggle with it in the beginning. So let me just go over it one more time. So when we're building the class or using the class from the inside is when we reference the this pointer. We don't have to, we just can if we need to, okay? So we're inside of the class and it gives us clarity about what we're referring to. Notice if we're in main, we've got a handy name for the class, right? So we kind of know what class we're talking about. When we're inside, it's kind of assumed, but maybe we need to be really clear about that. So that's really what it is. And it is a pointer. So it is followed by an arrow. So this arrow X from inside is referring to the data member X that's part of this class, okay? If I dereference it, remember the star. Star is like, if I'm not declaring a variable, it's like math again. It's like, hey, do something, follow that pointer and give me the whole box of groceries. That's what the star does to the this. It's like, hey, I want that. I want all of it. And then I'll do something with that whole box. So it's kind of a way of getting around the pointer from inside of the class, which is a little bit strange, but there are times when you might need to actually do that. And if you're curious, yes, you can do that. That is identical to this. In fact, when the compiler sees this, it converts it secretly into that. Dereference the instance and then follow it with a dot. Personally, I'd rather see this. This is called syntactic sugar. Many languages, their compilers or their interpreters give us humans syntax that we like in theory, and then they convert it into this before they actually make our final executable. So not critical. I never write code that way. That's like a gotcha question in an interview. You know, what's this? Oh, that's this arrow X, right? So we just got to break it down. Dereference the pointer, get me the instance. Oh, now I can get a dot. Same as that, right? Not that important, but just kind of puts this in context. Okay. Kind of fun stuff. Okay. And so if we think about, I just try to draw pictures in my head. You know, I always am seeing myself inside of the class and seeing this little pointer that's reaching out and pointing back at myself. We'll do some really cool stuff with our Facebook homework assignment, where this is going to be very cool, but somewhat tricky. So this is me, right? When I'm inside of there. Okay. If you understand it, you can do some really cool stuff. Okay. So we'll see that a little bit later. Okay. Here's our methods. Okay. Comparing two instances. So if I want to compare two instances, right? So let's take a look at this class. It's got a private thing similar to what we did. If I'm comparing whether the argument you gave me is greater than myself, and I know I just have one data member, my colors are a little goofed up. I'm going to return the answer to this question. Remember, this is a question. Is that this greater than that? True, false. Okay. So it's just going to return the answer to that question, right? So it's a good shortcut. You don't have to do the if else there. Just say return the answer to the question. Now, if I have lots of data members, it's a little trickier. So comparing or even sorting, for those of you who just took Comp 220, sorting instances of custom classes is not an easy thing to do unless we write some special methods. Like, how does C++ know whether one car is less than or greater than another car if we're making a car or a person or whatever? So we'll get back to that, how that actually works in C++. But here we can do a trivial comparison of our value, and then we know the answer to that question. Okay. So that's using this. Okay. So now we can just say, you know, see out 1 dot is greater than 2. On lecture 4 on Thursday, we're going to see that this is the secret way that people implement operators like star, times, minus between classes. So the exact functionality of this could be handed over to the less than symbol or the greater than symbol, right? We'll see how we do that in lecture 4. But once we understand how to do it here, it's a very quick step to make sure that it works with those symbols, which is really cool. Because then if you're making Pokemon classes, you can just plus 2 Pokemons together and get something brand new, right? So we'll see how all that stuff works on Thursday, which is really cool. That's called operator overloading. Got to do that, okay? So last couple things here. So if I create something and then I set it to a value, right? Just note that we don't need a constructor, right? If our default constructor is good enough, we can just skip it and just throw some methods in there. And C++ will construct T with a default value. It won't change it. So if I said X equals 1 here, right, then it would have a value of 1 for its X value, but you don't need to write the constructor, right? So that's kind of nice. We get a free one if we can get away with just default values. Okay. And if we ever wanted to return a pointer to myself, like, hey, give me a pointer, right? It's kind of silly, but I could create an instance, set it to a 12, create a pointer to an instance, and then say ptr equals t dot my pointer. That's like a really roundabout way of doing ampersand t. I could have just done ampersand t there, but just to show you how all the plumbing works, it's the same thing. Okay, it all ends up being the same thing. Okay. I know it's a lot. It's a lot. Hang in there. We're just about there. Okay. What if I want to return a copy of something? Okay. So star this says, hey, take a picture of me and send my instance back as a duplicate. So pushing it out the door, the return door here, forces it to make a copy of the same class that I am, okay? So I'm a this, so star this says get a copy of that and send it back. So that's a pretty cool way to implement a copy. We call that a shallow copy because it only really copies what the data members are in that moment in time. And we'll see what that means when we get to our homework 2, okay? Homework 2 or 3, I can't remember which one, okay? But that's an example of dereferencing to this so we get a copy of it and returning that, okay? So really cool stuff. Okay, so again, kind of breeze over this so we can kind of hit our mark at 7 o'clock. But you can come back and play around with this. You'll see if you try to run this program, it gives you a bad result, right? It's because we're not kind of using clear code here. So we need essentially to put the this in there so that we don't have ambiguity with this part. So I know we saw that, but just so you know, that's how we kind of solve that problem, okay? Or just change the name by putting an underscore in front of it, okay? Yes.
Clarify the difference between this pointer name and this dot name.
So we would probably never see a this dot because this is a pointer. And so if we put a dot after it in the context of in C++, I can't think of a situation where we do that. We could say star this dot that, right? So I think we had that earlier. So if I said parenthesis, dereference, that's my star, this, sorry for my bad scribbles, right? Parenthesis, dot, something, that's okay. That says take a snapshot and then reach in the box and get what's there. But I'm pretty sure if I did it, then it's probably a bug in there. But it should be just a star this if you ever see the dot in there. Okay. Good question though. Yep. So in here, a dot because B is an instance, right? B is just an instance. There's no star over here and no new or anything. Okay. All right, last one. Just a reminder, we kind of mentioned it before, but I was always curious about this. I'm like, what is the difference really? Right? Everything you can do with a class, you can do with a struct. It's just that by default, the permissions are biased in the other direction. Structs are kind of considered to be like totally public. So class members default to private in a class, structs default to public. That's it. That is the only difference. So if you understand a class, you understand everything. So that's why I really only focus on classes in class because it's super easy to just kind of go, oh, yeah, just skip the public private thing if you don't care about it in a struct, right? And you can have everything public for everybody all the time, okay? Okay. Otherwise, pretty straightforward, pretty much the same, okay? So you can kind of play around with that, but you can kind of see the difference here, right? So no need to really, these are all public, right? And we got to declare these public if we want them to be public, right? So that's really all it really comes down to. And I won't say much else about that for the rest of the semester because it's just that straightforward. Okay. Okay, that gets us to our lab a little early. And I know that was really dense, but that's like some serious glue, right? So if you slowly get to 80% of that in your head, you're in great shape. Okay, so for our lab today, we just kind of have that, you know, it's kind of like the array. I guess I forgot. I took it up one more notch. I'm being a little meaner than I thought. It's a linked list of nodes, kind of like the array, but it's a linked list. And it's got a next data member and a chest data member, okay? So what we need to do is kind of, first off, we need to remember how to go through a linked list, okay? And the last one's gonna be null, right? So we're gonna need a while loop there. So that's probably your first part. And if for each particular loop of the linked list, the chest pointer is not null, then we need to go down and grab the coins, okay? So a lot of people just give it a +1 for each one of these things, and that is not going to get you the right answer, right? We got to go inside of the class and add up the coins, okay? And I believe they're always going to add up to 100, okay? So if you don't get 100, I think you probably have a small problem there, okay? So we have our head, and while the head or while temp or some pointer is not null, we're going to loop around until we hit our null thing, okay? So we should kind of go down the path. And of course, at the end, our pointer is going to end up being null, but we should have finished adding everything up by that point, and we should get 100 coins, okay? I think, let's see. So let's take a look at our treasure chest, right? So this is my instance of the treasure chest that will be pointed to by chest in the node, okay? So you just got to follow the arrow in that case, not a dot, right? And then our node has a next pointer and a chest pointer, okay? So we will loop and move the next forward each time, right? And just check these and sum up whatever's in the coins data member of the chest, okay? And we'll take a look at the code here in just a second. So let me go back and just show you the code, the layout, in case my comments are not particularly clear, and then I'll let you guys get on with what you want to do here. So here's, we'll just jump to the code, right? So there's our chest, there's our node. So this is a prototype for something I've written, right? And this is what you are going to write below main, okay? So remember what we do, we put the prototypes up top and then we write the code below main. You'll see in a few lectures here why we've been doing that. But here's me building the list, linked list head, and then I pass that to your function and you return an answer, right? And it should be 100 coins, right? Okay, so let's take a look at what I'm doing. I won't bother you with this too much, but I pick a random seed so that I know everybody in the class is going to have the same results, right? And I just do a little bit of trickery to make sure I randomly sprinkle 100 coins around. So all you got to worry about is that I ultimately end up with 100 coins in there, okay? So, but you might find my code helpful, right? I have a do while for various reasons, right? And you're going to probably have a while loop, okay? So your while loop is going to start here. And there's your head pointer. And you'll probably need a variable to add up the coins, but don't forget to return them, right? So that's the answer to your function, okay? Questions on the lab? Okay. Well done. Thank you for not passing out. That was really, really, really dense, but we'll let you go with that. And let me know if you have questions. See you on Thursday. Okay. Thanks, everybody. Have a great week.